Okay, so we come back to ring theory exercises. So we continue with this one next. Exercise 21. Let R be the ring of real valued continuous functions on this closed bounded interval from -1 to 1. We have to show that R has zero divisors. We already know that this is a ring, and the addition and multiplication in this ring are of course this. Say f and g are two elements in R. Then each one of them is a continuous function with this interval as its domain. We then define f plus g and fg, sum and product of these two functions, with these formulas. F plus g at x is defined to be equal to f of x plus g of x, and just like that fg at x is defined to be equal to f of x times g of x. With respect to this addition and this multiplication, R forms a ring. And of course, from our usual results from calculus or analysis, we know that sums and products of continuous functions are again continuous functions. So that's why all the ring axioms are true in this case, which one can verify, of course. And so this forms the ring. Now we have to show that in this ring we have zero divisors, that is non-zero elements whose product is 0. So let's see. Consider the functions f and g belong, in the beginning itself, so we will mention it afterwards. Consider the functions. Let me write properly, that is like how a function should be written. This and g, don't confuse this f and g with this one, okay? That is just simply to show what the operations are. Given by the following formulas. Okay, so now we are going to define these two functions, which of course you can guess are going to be our non-zero elements in R whose product will be 0. F is defined like this. F of x is defined to be equal to x when x lies between -1 and 0, and is defined to be equal to 0 when x lies between 0 and 1. If we want, we can actually keep this possibility here also. There won't be any problem with the definition of the function. It will still be well defined. That is because when you put x equal to 0, whether you use this part of the definition or this part of the definition, you get the value 0 itself. So there is no conflict. So this is what f is, and G is defined to be, okay, wait, oh, so this is already negative. Now this will actually, we can take if we want this, but still just for the sake of, just for the sake of the graph, let us consider it as minus x in this part of the domain. And g of x is defined like this, partly of course just like f 0 here, and x here. In this case also we can keep this option, or if you find it somewhat disturbing, you can in fact just simply keep these two parts of the domain disjoint. Okay, now simply defining two functions is not enough for them to be in R, because R has not just functions defined on this domain, but those functions that are continuous. Okay, now there are of course different ways of showing that these two functions are continuous, which I am not going to go into. Instead, what I will do, I will draw the graphs of these functions. From the graphs you can see that they are continuous, which however should not be a part of the solution. I will just simply be showing the graphs as a demonstration. You will actually have to prove that these functions are continuous in this domain, which you can do in of course two ways. One is by applying the actual definition of the functions, and I did not mean to say actual definitions. Definitions of course we have to use, but the actual definition of continuity. The other way is to use the sequential formulation of continuity. That is, you take a sequence of points in this closed bounded interval which is convergent. Say xn converges to some number x in this interval. If you then manage to show that f of xn converges to f of x, and also g of xn converges to g of x, then that will prove that f and g are continuous. So which one of these you find easier, that is up to you. Whether you use the actual definition of continuity, the epsilon delta definition or limit definition of continuity, or whether you use the sequential formulation of continuity, it's up to you, but I'm not going to do that. So let us instead draw graphs of these functions. If the graph is not broken into, if the graph is in one piece in each case, then of course it's continuous. So let's see. We actually don't need much space for this. Let us first of all locate the interval. One, one, one. Okay, so this is minus 1, this is 1, this of course is 0, the origin, minus 1, 1. So let us first of all look at the graph of f. So you can see that in this part of the domain between minus 1 and 0, the formula is actually that of a linear function. So it is going to be a straight line, we already know that. And the straight line will pass through two points, two particular points. Let us see what those points are. When x is minus 1, then f of x is 1 because minus of minus 1. So that means this is 1 point. And when x is 0, then f of x is also 0. So this is the other point. So in this part, the graph is just simply this straight line. And in this part, the function is constantly 0. So that means the graph is just this line segment on the x-axis. So this is the graph of f, y equal to f of x, and it is continuous. It is not differentiable at this point. There is a sharp corner, but that is a different thing. It is unbroken, so it is continuous. On the other hand, when we draw the graph of g, in this part of the domain between minus 1 and 0, it is this horizontal line segment on the x-axis, and in this part it is just simply y equal to x, whose graph we already know. It's this line that makes an angle of 45 degree with the positive direction of x-axis. So here also it's an unbroken, actually it's two lines, but it's not a broken structure. So that's why this is also continuous, y equal to g of x. But I repeat that you have to rigorously prove or somehow justify that these functions are continuous, either by using those two things. You use the definition of continuity as such, or you use the sequential criterion for continuity, or there are other ways also. Whatever you do, you have to show that, and that is not like this. You cannot just simply draw graphs and say, okay, this is continuous. No. So once you do that, then you can say that, okay, f and g are elements in the ring R, and then you can proceed further. I am just simply going to write here clearly f and g belong to R, and there is one more thing, f and g are both non-zero. Now what do we really mean by this zero here? This zero is of course not the real number 0, but the zero function, the function that is constantly 0 on this closed interval, or in other words, the function which is the additive identity in this ring, the 0 element, that thing. And we can clearly see why f and g, neither of them is 0, because we have non-zero values for both f and g. That's why. Now for any x belonging to this closed interval, we have x belongs to -1, 0 or x belonging to 0, 1. If x is in minus 1 comma 0, then g of x is equal to 0. This is one thing. The other possibility is if x belongs to 0 comma 1, then f of x is 0. Hence, in any case, when we calculate fg at x, which by our definition of product is f of x times g of x, that is going to be 0 always. That means the product function fg is identically 0. This is equal to 0. That is, the function fg equals the function constantly 0, or the additive identity. Hence, f is a zero divisor in R. Actually, G is also a zero divisor, but it's enough to write just simply about F. So that's just it. We had to show that R has zero divisors. We have shown that it has one, and that's it. Next, prove that if A is a ring idempotent, okay, if element A is a ring idempotent, then the nth power of A is always equal to A for all positive integers n. For all positive integers n, that means we can apply induction, and we will do that. This one is not very difficult. Solution, we apply induction. I am losing ink fast. Let me just refill. We apply induction on n. When n is equal to 1, then of course our claim is true. Suppose this is true, for some positive integer n. Then we need to show that the n plus 1th power of a is also equal to a. Now this can be written as this. Okay, now keep one thing in mind, that here we are not using any, of course we are using a rule of exponent, like we have two rules of exponent, but the rule of exponent we are using here to write this n plus 1th power as the product of this nth power and a is not coming because we are in a group. No, we are in a ring where actually the operation that is involved in this is the ring multiplication. Now with respect to the ring multiplication, no ring is actually a group. And well, you can of course consider the zero ring, but that is just a trivial possibility. That is because inverses, multiplicative inverses may not exist. For example, in the ring of integers, only two ring elements have multiplicative inverses, 1 and -1. None of the other integers has a multiplicative inverse in the ring itself. So the thing that you see here is true nevertheless, but it is not coming from our usual group theory rules of exponents. It has to be proved, and it can be proved in a very trivial manner, again using induction, but it is not coming from a group. That's what I wanted to say. Okay, now using our induction hypothesis, this is A. That means we are having A squared, and now you use the fact that A is an idempotent element. So that's why A square is equal to A, and this completes the induction. And proves the claim. Next, determine all ring elements that are both nilpotent elements and idempotents. Okay, that are both nilpotent elements and idempotents. Okay, let A be a ring element that is both nilpotent as well as idempotent. and idempotent. Okay, so being nilpotent, a power of a will be equal to 0 where the exponent is some positive integer. Since a is nilpotent, a to the power n is equal to 0 for some positive integer n. But at the same time a is idempotent also, so we can very nicely use the result of the previous exercise. Since a is idempotent to the previous exercise gives us a to the power n is equal to a. So you now combine these two equations. Thus, this is equal to 0. So in any ring, the only element that is both nilpotent and idempotent is the 0 element. That's just it. Next, find a zero-divisor in this ring. Set 5I, whose elements are of course elements that look like this: a plus ib, complex numbers. Oh well, I should not say complex numbers, sorry, because a and b are not real numbers. Objects that look like complex numbers, where a and b are coming from this finite field Z5. Note that, so it's just simply we produce one nilpotent element and zero-divisor, and that's just it. Note that 3 plus I and 2 plus I belong to this ring, such that if we take their product, then what do we get? 3 times 2 is 6 plus I square is minus 1. I mean, although the things that we see here, that is this, if we call them real and imaginary parts, just for the sake of explanation, the rule for multiplication is same, just like you ordinarily multiply complex numbers. So 3 times 2 is 6 plus I square is minus 1, so this is 6 minus 1, and 3i plus 2i is 5i. That means you get 5 plus 5i. But the thing is that with these coefficients, these numbers, you have to keep in mind that they are being manipulated in Z5. So in Z5, 5 is equal to 0. So that's why we get 0. Whereas none of these two things is equal to 0. We need to mention that also. Note that 3 plus I and 2 plus I are both non-zero. Non-zero in Z5I. Hence 3 plus I is a zero-divisor. Sometimes zero-divisors, rings which have zero-divisors are looked at, they are considered to be somewhat pathological, because you are multiplying non-zero elements and you are getting 0. That runs counter to our intuition. However, they are of course there. The definition of ring and its generality allows them to be rings, and they are sometimes interesting in their own right. Okay, so this is one thing, and let us solve one more. Everything need not always be applicable somewhere. That's not the main goal. The main goal is to study the thing for its own sake. Then additionally, if it has application somewhere within the theory itself, or outside of the theory, or even outside mathematics, that is a bonus. Find an idempotent in again that same ring. And this itself, 3 plus I will turn out to be an idempotent element. Okay, let's change the language. We have this such that, so we calculate its square. So its square will be 3 square minus 1, that is I square, plus 6i. But then you adjust everything in Z5. So 9 minus 1 is 8, but because we are calculating modulo 5, our modulus is 5. So 8 is equal to 3 and 6 is equal to 1. So that's how you are getting the fact that the square of the element is equal to the element itself. So that's why it's idempotent. Hence is an idempotent. Sometimes we people in mathematics are we become tired all the time explaining where our results are applicable. But this constant query of things being applicable is not just tiresome, but it is in a sense stupid also. You have a very beautiful flower and you are asking where is it applicable. It's just like that. Okay, anyway, so I end the things here itself for tonight. Tomorrow we again have analysis, and we are going to see further things about series of non-negative real numbers. We have already seen one or two things, and we will see more things. So that's just it. So I wrap things up. So see you tomorrow with real analysis. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.